Hello everyone, wishing you all a very good morning and welcome to today's class. Well, let us have a quick recap of what we had done in the last class. Today, as I think, we are supposed to do lecture number 22. Let us have a quick recap of what we had done in lecture number 21. And as far as I remember, in lecture number 21, we had seen the formulae for gravitational potential energy for extended bodies for a point mass of mass m at a height h. The gravitational potential energy is mgh. Then we had seen the gravitational potential energies of rod, a uniform rod. We have to find its center of mass. What is center of mass? Well, right now it is the center of the body. We'll come to know about the center of mass in the coming chapters. We also had seen the center of mass for a uniform chain or a wire. It also lies at the center of the body. We also had seen the center of mass for a ring or disc or a sphere. I also told you the difference between a sphere and a spherical shell. We had seen some problems based on this. Then the last problem, I think, was problem number 51 from your notes, that what work has to be done to lift a rod which is lying and make it upright, vertical. This work has to be done by the external force. Here it is not mentioned that the change in kinetic energy is zero, but you will have to understand that such questions always will have change in kinetic energy as zero. Do you all understand this? Up till here it's clear. Can I have some raised hand that up till here it's clear, sir? You don't have any doubts up till this point? If you don't have doubts up till this point, then we will move on to the first thing of today's class. And the first thing of today's class starts from here, which did we do problem number 52 in the last class, where we had a rod. We had a rod and it was hinged at a point and it was turned by an angle of theta. We found out how much is the change in the gravitational potential energy. Did we do this problem number 52 in the last class? I'm just a bit confused. I feel that we have done this problem. We had called this angle as theta. We had called the mass of this rod as m and the length of this rod as l. And we had found out that the change in gravitational potential energy for this rod is always equal to mg into L by 2 into 1 minus cos theta. Do we remember this? Have we done this question? mg L by 2 into 1 minus cos theta. Can I have some raise hand that we have done this question?
Yes, sir.
Okay. If we have done this question, that is great, because then we have done almost all the questions that are to be done. Now we can write this next heading, and this next heading goes by the name of work done in pulling a chain against gravity. These type of questions, they come in more than one form. We are not going to solve how these questions are going to come, because we will just try to understand and remember the formula, and that is good, more than enough. I'll try to explain how this question or how this answer is achieved. So what do we have here? If I can just elaborate, I hope you have written the heading, work done in pulling a chain against gravity. I hope all of you have written this heading. Now, once you have written this heading, you have to understand the premise of this question. And the premise of this question is very simple. I have a chain of mass m and length l. Total length is l. Some part of this chain is on the table, horizontal table, which you can see, and some part of this chain is hanging. As you can see, L by N part of this chain is hanging. If N is 2, it cannot be 1, because if N is 1, the entire chain is hanging. If N is 2, half of the chain is hanging, half of the chain is on the table. If N is 3, 1/3 of the chain is hanging and 2/3 is on the table. If n is 4, 1/4 of the chain is hanging and 3/4 of the chain is on the table. So it is kept like this. What we got to do is we got to lift it up. What do you mean by lifting it up? The entire hanging part should also come and lie on the horizontal table. So this is what we got to do, and this is known as work done in lifting up a chain against gravity. So this is the diagram that you are going to draw. Some part of the chain is on the table, L by N part of the chain is hanging, and we have to find out the work done in lifting this chain. I will give you a minute to draw this diagram. I hope you have drawn the diagram. The diagram was pretty simple. Now, how do we solve this question? What is the work done in pulling this chain against gravity? Remember what we have assumed here, and that you must always remember that the chain in kinetic energy will be zero. So we are going to lift the chain very slowly. Now again, remember, if I make the change in kinetic energy zero, what will happen is work done by external force, which is what we have to find out here. Where is the external force? This hand that you see is the external force that is going to lift this chain. That is going to lift this chain. Now, if the change in kinetic energy is zero and there is no friction, nothing else is there, then this work done by this external force will be negative of work done by gravity, and that will be equal to change in the gravitational potential energy. So you find the gravitational potential energy of the hanging part, you find the gravitational potential energy of the part which is on the table. It is a simple thing to do it. Once you do it, you will get the answer for work done in pulling this chain against gravity. I'm not going to go into how that answer is achieved. I've already told you the calculation part I am not going to do because that will not serve any purpose. What we are going to do is now note down what is the answer that comes finally, and the answer that comes finally is this. This is the work done by the external force in lifting this chain up on the table. Remember, this thing is done without any change in its kinetic energy, so this will be equal to negative of work done by gravity, and this will be equal to the change in gravitational potential energy. Do we understand this? Can I have some reason that we understand this? So you have to remember the heading, you have to remember the diagram. N part of the chain, 1 by n part of the chain is hanging. If n is 2, half is hanging. If n is 3, 1/3 is hanging. Can I have some raised hand from the girl sitting on the right? Boys on the left, do you understand this, boys? I hope you have noted this down. So this is one thing that you must remember. You can always derive it from the work done due to external forces, but it is good if you can remember this. That is the first part of today's class, of remembering work done in lifting up a chain against gravity. I'll give you 1 minute to note this down, and then we will move on to the next heading. I hope all of you have noted this thing down. The next thing would be the reverse of this, sort of a reverse of this. Velocity of a chain while leaving the table. Now, in first case, what we had done is this chain was hanging, L by N part of the chain was hanging, and we were trying to lift it up and put it back on the table. Right now, what we are doing is 1 by N part of this chain is hanging, and somehow we are holding the chain. We are holding the chain. Now, instead of lifting the chain, what we are going to do is we are going to leave the chain. We are going to leave the chain. Once we leave that chain, what will happen? There is no friction. So what will happen once I leave the chain from here? What will happen if I leave the chain from here? The chain will just fall down. Yes or no? Can I have some raise hand that the chain will fall down?
Yes, sir.
Okay. Now, when the last link of the chain leaves the table, as you can see in the next diagram, the last link of the chain is leaving the table. Since this chain is accelerating, it will have a velocity while it leaves the table. At that time, the velocity of any of the links of the chain will be same. So we have to find out the velocity of the chain, which is the velocity of the last link as it leaves the table. So what I'll do is I will ask you to draw this diagram first, and then again how it is done. Again, it is done by using work energy theorem. I'll ask you to draw this diagram. This is case number 1. You are holding the chain, L by N part of the chain is hanging. Then I leave this chain. This is the initial condition number 1. This is the final condition number 2. The chain is moving. The chain is moving down with a velocity v. All parts of the chain are moving with a velocity v. We have to find out the value of this velocity. How it is done? Again, work done by gravity is change in kinetic energy. That is the formula that we will apply. We'll apply the work energy theorem. We'll apply the work energy theorem and get the answer of the velocity of the chain while it is leaving the table. I'll give you a minute to draw this diagram, and then we will note down the formula and try to remember it. Well, I hope you have noted down the diagram. Once you have noted down the diagram, you simply can note down the velocity of the chain as it is leaving the table. Velocity of the chain as it leaves the table is given by this formula, root over GL into 1 minus 1 by n square. You just need to put the value of n. If n is 2, it will be 2 square, 4. If n is 3, It would be 3 square, 9, and so on. Just note down this formula. How is this question solved? It's no rocket science. We'll just apply work energy theorem, work done by all forces. Here, all forces include gravity and normal reaction. Normal reaction does not do any work. All work is done by gravity. Work done by gravity will be changed in kinetic energy. That's all. That's all you need to do. Remember this formula. Two formulas I've given. One is work done in lifting up the chain. Number two, velocity of the chain as it leaves the table. I hope you have understood this formula. I hope you have understood this formula and you will remember them. I hope everyone has noted this down. Can I have some raise hand? Have you noted this down? Boys at the back, girls at the back. Okay. If you remember this down, if you have noted this down, these are simple questions that you have to do. Problem number 54, as you can see, it has come in IIT many number of times. It has come in IITree as well. It can come at any time, at any point in life. So the question is very simple. A uniform, read the question once, mark down important points, solve the question. Length is L, mass is M, is lying on a smooth table. 1/3 of the length is hanging. So N is equal to 3. Vertically down the edge of the table, if G is the acceleration due to gravity, what is the work required to pull the hanging part on the table? So as you can see, 1/3 of the chain is hanging. What is the work done in lifting up this chain onto the table? I'll give you a minute to solve this question. Straightforward question, does not require rocket science. 1 minute. So I hope all of you have done this. This is just a way to remember the formula and to apply it. What is the work done in lifting up this chain? It is simply mgl by 2n square. That is the formula that we have seen. Here the value of n is simply 3. Just put the value of n as 3 and you will get the answer as mgl by 18. All of you got this answer? Can I have some raised hands? Simple question, straightforward question. The same question could very well appear in the exam in 2023. If it does come, well, you know the answer straight away and you can do it very, very fast. One more question we will do so that the other formula also becomes familiar in your head. Problem number 56. Uniform chain of length 2m, length 2 meter, is held on a smooth horizontal surface. Half of it is hanging over the edge. If it is released, find the velocity with which it leaves the table. 2 meter length, half of this is hanging. With what velocity does it leave the table? You can take the value of G as 10 just to simplify your answer. I hope all of you can do this. I'll give you a minute to do this. Well, I hope all of you have done this. Just have to apply the formula. Formula is V is equal to root over GL into 1 minus 1 by n square. Value of G is 10. Length of the chain is 2 meter. Half of this is hanging, so n is equal to 2. You just put the formula and you will get the answer as V will be equal to under root of 15. You can find the value of under root of 15. Approximately it is coming as 4 meter per second, and that is the answer that we are looking at, approximately equal to 4 meter per second. Do we all get this? Can I have some reason that we understand this? Everyone understand this? Boys at the back, boys on the left, girls on the right. Everyone understand this?
Yes, sir.
Okay, that is great. Now these are the questions. If you can do them on your own, well done then. Now let us move on and come to the next important part of this chapter. And the next important part of this chapter deals with, all of you know that, something known as law of conservation of energy. So that is the next heading that we are going to write. Law of conservation of energy. I'll give you a minute to note this down and think about this. Then I will start asking questions on this topic. Law of conservation of energy. Write the heading. I'll give you a minute. Well, I hope you have noted down the heading. Now,
Yes,
do you have
sir.
any idea what is law of conservation of energy? You must have heard this term, law of conservation of energy. Can anyone tell me what is law of conservation of energy? Anyone? You know this? Everyone knows this. Fifth standard, sixth standard, seventh standard. You've heard this. What is law of conservation of energy? Anyone? No one knows it? No one? That would be sad. Surprising as well. If you don't know what is law of conservation of energy, I would be very surprised. No one knows it? Cannot happen. Yes, tell me what is law of conservation of energy? You know it. I know that you know it. All of you know it. Tell me what is law of conservation of energy?
Energy cannot be created nor destroyed.
Yes, it simply says that energy cannot be created. Energy can't be created. Energy can't be created or destroyed. Then what can happen with energy? Then what can happen with energy? You can't create it, you can't destroy it. Then what you can do? You can do nothing about it. Or can we do anything about it?
Converted from one form to another form.
Yes, it can only be converted. It can only be converted from one form to another. Yeah, to other form. You cannot create energy, you cannot destroy energy, you can only convert it from one form to another. Right now, there are lights on in this room, bulb or your tube light. What it is doing? It is converting electrical energy into light energy, converting energy from one form to other. Your car, when it runs, you put in fuel. Fuel has got chemical energy. That chemical energy, because of an explosion, internal combustion, it gets converted into kinetic energy and your car moves. Basically, whatever we see around you, an electric pump is converting electrical energy into mechanical energy. It is pumping your water, electric pump or electric motor. Everything that you see around you is a sort of a machine which is basically converting energy from one form to another. And if you can trace the source of all this energy that we use on earth, whatever energy we use on earth, from where it is coming ultimately, what is the ultimate source of energy for our planet earth? Any idea from where all this energy is coming that you see around you? Electrical energy, mechanical energy, from where it is coming? The ultimate source of energy for earth is sun, the dear sun, where this nuclear fusion reaction is happening. Hydrogen is getting converted into helium and it is giving out a lot of energy. That energy comes in the form of sun rays and this gives life to earth. We cannot create energy, we cannot destroy energy. Energy can only be changed or converted from one form to another. This is law of conservation of energy. I hope every one of us understands it. Now, this law is never violated. It is always true. Whenever you have anything happening, energy of that system always remains constant. Energy of the universe always remains constant. Sometimes it is converted into some form which is of no use, and then we call that energy has been lost. Energy is not lost. It is converted into some other form which may not be of useful, which may not be useful. For example, if you have two cars moving towards each other and these two cars colliding, before collision they have very high kinetic energies. When they collide, they stop, the kinetic energy is gone. But then what happens? When they collide, you hear a big noise, sound energy. You might hear sparkles coming, light energy. Then these cars get heated up a lot, heat energy. So the entire kinetic energy is converted into these forms, which may not be of use for us, but energy always remains conserved. We are still to find out a process where energy is created or energy is destroyed. This is the universal truth. Right now, this is the universal truth. You cannot create or destroy energy, whatever process you do. Energy of the universe, when the universe began as a big bang, whatever energy that universe had, the same energy is there present in the present day universe. Nothing has changed. That is law of conservation of energy. But now what we are going to hear, what we are going to do is understand a term which is known as mechanical energy. Have you heard this term mechanical energy? You can write it as short form as ME, mechanical energy, ME. What is this mechanical energy, anyone? We have created this term which is known as mechanical energy. And what is this mechanical energy? Sum of Potential energy and kinetic energy is known as mechanical energy for a body. So if I sum up your potential energy as well as your kinetic energy, the energy that I get is known as mechanical energy. Now you must remember while you are summing that this potential energy can be of gravitational type, it can be of spring or elastic potential energy, or it could be of electrostatic nature. Whatever potential energy is there, you may have only one type of potential energy, you may have two types of potential energy, you may have three types of potential energy. All these potential energies together plus your kinetic energy is known as your mechanical energy. Am I clear about this term, which is known as the mechanical energy of a body? Can I have some reason that we understand this? Okay, I'll give you a minute to note this down. I hope you have noted this down. If you noted this down, then comes the next heading, which is the most important heading of this chapter: law of conservation of mechanical energy. In short, I call it LOCME. LOCME. What is this LOCME? Anyone? Any idea about law of conservation of mechanical energy? Remember,
Sir,
this is not the law of conservation of energy. Law of conservation of energy is always valid.
sir,
Yes, beta.
sir, for an isolated system or body in presence of conservative forces, the sum of kinetic and potential energies at any point remains constant through the motion. It does not depend upon time. This is known as law of conservation of mechanical energy.
That is absolutely correct. Well done. Law of conservation of mechanical energy. You must remember, if only, no, it's a condition here. If only conservative forces are present, if only conservative forces are present, and non-conservative forces are absent, if I call it absent, in some cases, I think in the chapter on rotation, you would have found out that when a ball is rolling, for ball to roll, normally you require static friction. For a ball to roll, there is static friction. Now, if there is friction, there is a non-conservative force present, but you can apply law of conservation of energy in case of a rolling body. It is still valid, even though there is friction present, a non-conservative force is present. Even then, you can apply this law of conservation of mechanical energy, even though friction is present, because work done by that friction is zero. So I'll add two conditions here. First condition is only conservative forces are present. Second condition is non-conservative forces are absent. Third condition is or their work done by non-conservative forces NC is 0. So even if they are present, their work done is 0, which is the case of a rolling ball. In case of a rolling ball, friction is present. It is a non-conservative force, but still the work done by that friction is 0, and hence you can apply law of conservation of mechanical energy. So what does the law of conservation of mechanical energy say? If only conservative forces are present and non-conservative forces are absent, or their work done is 0, then wrong color, then the mechanical energy of the body, which is the sum of potential energy plus kinetic energy, remains constant. This statement is known as law of conservation of mechanical energy. This statement is known as law of conservation of mechanical energy. Mechanical energy of the body, which is potential energy plus kinetic energy, remains constant. Or mechanical energy at point 1 will be equal to mechanical energy at point 2, which would be a constant. But remember, whether I write it as equation number 1 or I write it as equation number 2, equation number 1, equation number 2, they are only valid. When are they valid? Both the equations. They are only valid. They are only valid when only conservative forces are present. Only conservative forces are present and non-conservative forces are absent, or work done by these non-conservative forces is 0. So this condition has to be fulfilled for law of conservation of mechanical energy to be true. Conditions are conservative forces should be present only, non-conservative forces should not be there, or the work done by non-conservative forces must be equal to 0. I'll give you a minute to note this down. Then I'll note down the smaller points here, summarize them, and then probably we'll wind up the class today with this information. In the next class, we will be solving questions on law of conservation of mechanical energy. 2 minutes for everyone to note this down. I hope you have noted this down, everyone. Yes or no? Can I have some raised hands that you noted this down? Okay, what I'll do is, again, I'll try to summarize all the important points. Important points about LOCME. What is point number one? It is only valid under the following condition. So there must be conditions met. It is only valid under the following condition. What are the conditions? Condition number A. What is the first condition for mechanical energy conservation to be valid? Only conservative forces are present. Number two, non-conservative forces are absent. Same thing I can write in a different way. Work done by non-conservative forces is zero. If all these three conditions are met, then LOCME is valid. If work done by non-conservative forces is not equal to zero, then LOCME is not valid. You cannot apply LOCME if there are non-conservative forces present and their work is not equal to zero. You cannot apply LOCME. Then what do you do? Remember, LOCME is the daughter theorem. Now, what is this son and daughter and mother and daughter funda? LOCME is daughter theorem. What is this daughter theorem? If this is the daughter, there has to be a mother. Then who is the mother? If LOCME is the doctor, not the doctor. If LOCME is the daughter, then who is the mother? Work energy theorem, work kinetic energy theorem is the mother theorem. Work kinetic energy theorem, the blue, is the mother theorem. The mother gives birth to a daughter, not the other way around. Daughter does not give birth to a mother, not till now. So, work energy theorem is the mother theorem. LOCME is the daughter theorem. That means, wrong color. That means LOCME is derived LOCME is derived. Okay, the spelling is wrong. Let me correct it. LOCME is derived from work energy theorem. So law of conservation of,
Karthik,
yes beta, am I audible and visible to all of you? So LOCME is derived from work energy theorem. It is a part of work energy theorem. What is work energy theorem? What is work energy theorem? Anyone? Now this work energy theorem is valid in all cases. Work energy theorem is valid in all cases. So basically what I mean to say here is work done by all forces is equal to change in kinetic energy. This is my work energy theorem. This is valid in all cases. What do you mean by all cases? Whether they are conservative forces present, it is valid. Whether they are non-conservative forces present, this is valid. There can be a case where both conservative and non-conservative forces are present. Work energy theorem is still valid. And therefore, I call it, which theorem? I call it the mother theorem. It is the mother theorem. Always valid. Mother theorem, always valid. But if I come to LOCME, which says that mechanical energy of the body is constant, this is my LOCME. This is my LOCME. It is only valid if conservative forces are present. If only conservative forces are present. Non-conservative forces absent, or work done by non-conservative forces is zero. These conditions must be met. For work energy theorem, it is valid in all cases. But the daughter theorem, the green theorem, the daughter theorem, the green theorem, there's something wrong. Let me just correct it. Okay, the green theorem is only valid if conservative forces are present and non-conservative forces are absent, or their work done is zero, and therefore I call it the daughter theorem. Do we understand this? What is happening here? We can always apply the work energy theorem in all the cases. Don't have to worry. You can apply work energy theorem in all the cases. This is my work energy theorem. This is my work energy theorem. You can apply it on all the cases. Don't have to think whether conservative forces are there or non-conservative forces are there. Apply it wherever you feel like. Mother theorem. But the daughter theorem, which is LOCME, the daughter theorem, which is LOCME, can only be applied if non-conservative forces are absent. Do we understand this, everyone? Just remember these points about the work energy theorem. We'll continue with this work energy theorem, and LOCME will do a question by both the ways so that you understand whatever questions can be done by the work energy theorem, they can be done by LOCME, but whatever questions can be done by whatever questions can be done by LOCME daughter can be done by work energy theorem. But if non-conservative forces are present, questions can only be done by work energy theorem. They cannot be done by LOCME. This is what you need to remember. LOCME can only be applied if non-conservative forces are absent. Work energy theorem is the universal theorem. That means you don't need LOCME to solve any problem. because you already know work energy theorem. But in some cases, when the non-conservative forces are absent, it is easier to apply LOCME rather than, I mean, both are same, but it is easier to think about LOCME. And that is why we will be applying LOCME in the problems that are going to come ahead in the next class. This is all from my side for today's class. I hope you loved it, enjoyed it. See you tomorrow, day after tomorrow with the new class. We'll be dealing with law of conservation of mechanical energy. And now non-conservative forces will not come, only conservative forces will come. So see you then. If you have any problems, please ask. Else, it is a wrap from my end. I hope you loved the class. See you. Study hard. Don't waste your time. Bye bye.